Good morning, good afternoon, and good evening to the online participants from all over the world that are watching this video. I am honored to have been invited by CIRCAS to contribute to the virtual school in terrestrial reference frame, geodynamic and atmospheric monitoring, to talk about zenith total delay estimation in regional and international networks and its contribution to climatology and meteorology. This presentation is divided into 4 sections. In the first section, I will give an overview of the IAG international and regional ground-based networks. The second section will focus on the tropospheric estimation, how we get zenith total delay and integrated water vapor from the observation. In the third section, I will show example of tropospheric monitoring at ground-based networks with a focus on EPN activities. In the last section, requirements and application to climate and meteorology will be provided. The IAG services, the International GNSS Service, the International VLBI Service, the International DORIS Service, and the International SLR Service generate products by collecting and analyzing their own observation, relevant for geodesy and for other sciences and applications. Accuracy and robustness of the products, quality control, timeliness, and state-of-the-art quality are the essential aspects of the services. We will focus on the 3 microwave techniques: GNSS, VLBI, and DORIS, whose activities are organized and coordinated in the framework of the IAG services, IGS, IVS, and IDS. Each service has a ground-based tracking network that is one of the permanent components, along with operations centers, data centers, analysis centers, a central bureau, and a governing board. The IGS network is made up of more than 500 permanent and continuously operating stations distributed worldwide. The IVS network has about 40 legacy stations and 15 BGOS radio telescopes. The IDS network is about 60 stations. There are locations where the geodetic techniques are co-located. The collocation is important because it enables the integration of individual technique-specific networks into a unique terrestrial reference frame, the assessment of the observation quality and accuracy. The connection of tropospheric parameters between co-located GNSS station and VLBI radio telescope takes place by means of what we call the tropospheric tie, namely the difference between the atmospheric condition quantified as zenith delay of collocated instruments due to the height difference. In the previous slides, I have shown international ground-based networks, but there are also several regional networks covering, for example, Europe and the Americas. On the left-hand side, you can see the Europe Permanent GNSS Network. As of today, EPN is made up by 424 GNSS tracking stations in Europe. It is operated under the umbrella of the IAG Regional Reference Frame Subcommission for Europe. On the right-hand side, you can see the CIRCAS network, which is made up of about 400 GNSS tracking stations in the Americas and in the Caribbean, operated under the umbrella of the IAG Regional Reference Frame Subcommission for South and Central America. This brings me to the second part of this presentation. I will focus on the tropospheric estimation, how we get zenith total delay and integrated water vapor from the geodetic observation. In this slide, you can see a schematic presentation of individual slant path delay from 3 GNSS satellites and their mapping into zenith total delay. On the ground, there is a GNSS antenna in the middle, a VLBI radio telescope on the left, and a Doris beacon on the right, being the signal of the 3 microwave geodetic techniques delayed by the neutral atmosphere in the same way. In the case of VLBI, we know that the signal is transmitted by a quasar that is not shown in the picture. Such a delay is a noise for geodesy, but is a signal for climate and meteorology. Let us focus on GNSS data processing to figure out how, from the collected data, we estimate tropospheric parameters. The first thing we need are the GNSS observations collected at the ground stations. For analyzing them, we need corrected and updated metadata stored in station site log. We need models, auxiliary informations that are satellite products, this last coming from a global processing. For GNSS data reduction, we need a scientific software at the state-of-the-art with a proper setup for the estimation of tropospheric parameters. When the tropospheric parameters are output of the data processing, a post-processing phase is needed, for example, to detect outliers and to homogenize a long-term ZTD time series in case of climate application. It is important to keep in mind that the delay is not observed, but it is estimated. That means that its accuracy depends on the accuracy of all the other parameters used during the data processing. ZTD can be converted into integrated water vapor, an essential climate variable of the World Meteorological Organization Global Climate Observing System, if auxiliary information, namely pressure and weighted mean temperature of the atmosphere, are available. In the third part of this presentation, I will report on tropospheric monitoring at ground-based network, focusing on EPN and IGS. As of today, EPN is made up of 424 stations. These stations are distributed among the analysis centers in such a way that each station is analyzed by at least 3 of them. This ensures the reliability of the EPN products. In addition to the site coordinates, the analysis center estimates tropospheric parameters, namely ZTDs and horizontal gradients, at 1 hour sampling rate. The individual analysis center solution are the input of the combined EPN products, containing the combined tropospheric estimates with an hourly sampling rate of all the EPN stations. For a single site, ZTD is modeled as the following equation, where Yn is the true ZTD at epoch Tn, Bk is the analysis center bias, and Ekn is the residual between Yn and Ykn. The linear function model can be solved in a generalized least square sense by adding the following constraint equation. The method provides combined ZTD estimates and their standard deviation, site and analysis center specific bias and weight. On a weekly basis, the monitoring is done at analysis center level and at the station level. In the upper part of the plot, you can see the ZTD bias of each contributing solution with respect to the combined solution. The related standard deviation is in the lower part of the plot. This plot shows the performance of each analysis centers with respect to the combination. It helps to identify potential periodic signals and reflect changes, for example, in the used option, analysis procedures, and so on. Such changes are clearly seen in the time series that is made up of two pieces, EPN, repro-true, and operational. The operational time series is made up of two pieces as well. The first is in IGS 14 standards, the second in IGS 20 standards. This time series is not homogeneous, so it is not useful for climate application. It will be replaced by a completely reprocessed time series in IGS 20 standards that will be delivered in the framework of the third EPN reprocessing campaign. Similar monitoring is done at station level. This example is for the Swiss station Zimmerwald, that is one of the two EPN stations analyzed by 7 EPN analysis centers. On the right side of the slide, you can see the plot of the ZTD bias upper part and related standard deviation lower part of each contributing analysis center processing Zimmerwald with respect to the combined solution. What the IGS is doing in the field of tropospheric monitoring. The IGS associate analysis centers generate tropospheric products for all the stations in the IGS network. These products include 5-minute estimates of zenith total delay and north and east tropospheric gradients component. It's a PPP solution, not a combined one, that utilizes the IGS final satellite orbit and clock products along with the EOP product. They are available with a latency of 3 weeks following the observation day. The last section of this presentation is devoted to the requirements and application to climate and meteorology. Let's start with climate. The climate requirements are long-term time series. Climatology is based on 30 years, global coverage, dense regional coverage, and homogeneity. We need homogeneity in the processing option, in the instrumentation, in the auxiliary meteorological data used in the conversion in the ZTD to integrated water vapor conversion. The applications can be divided into 3 areas: numerical weather prediction reanalysis, climate model validation, exploitation of integrated water vapor time series. As far as numerical weather prediction reanalysis is concerned, a reanalysis is made using a fixed numerical weather prediction model with data assimilation for a long period in the past. Reanalyses are used to estimate trends in climate. The better quality observations are, the better the reanalysis is. GNSS-based atmospheric estimates are assimilated in today's reanalysis. Climate model validation. A climate model includes an extended numerical weather prediction model which can run without data assimilation for a very long period without becoming unrealistic. Running a climate model for a past period, observations including GNSS-based data can be used to assess the skill of the climate model. That way, climate models can be improved. Exploitation of integrated water vapor time series. Water vapor is of enormous importance in the climate system. Instead of using reanalysis data, one can directly study integrated water vapor time series to understand time and spatial variability in the water vapor field, study integrated water vapor extreme, long-term trends, relationship between integrated water vapor and precipitation. Deducing integrated water vapor data about pressure and temperature from the observation or from a numerical weather prediction model. High-resolution European regional reanalysis for Copernicus Climate Change Service is made using numerical weather prediction harmony aroma model that is used operationally at many Met services in Europe, including the Nordic countries. It encompasses conventional observations, satellite radiance, data from aircraft and buoys, scatterometers, atmospheric motion vectors, GNSS radio occultation, and EPN ZTD data. This plot on the left shows in red the control run with no GNSS ZTD, and in green the same run with the GNSS ZTD. For verification of specific humidity, the verification of specific humidity is done against radiosonde. The outcome is that the model is generally too dry and that GNSS ZTD monitors the model at all levels. As far as meteorology is concerned, the requirements are expressed in terms of accuracy, timeliness, spatial coverage, horizontal sampling. For each of them, there are three values: the threshold, the minimum requirement, the optimal, the ideal requirement, and the target, an intermediate between the threshold and the optimal. In the upper part of the slides, the requirements are for hourly ZTD product for global and regional numerical weather prediction, while in the lower part, they are for sub-hourly ZTD product for nowcasting and local numerical weather prediction. The operational use of GNSS data in Europe is done under the EGVAP umbrella, 20 years of collaboration between the geodetic and atmospheric communities. On the left, you can see the European stations, and on the right, the global stations that are contributing to EGVAP. EGVAP is the EUMETNet GNSS water vapor program. The main purpose of EGVAP project is to collect and distribute GNSS-derived ZTDs for usage in operational weather forecasting in near real time within 90 minutes. There are 25 analysis centers, mainly from geodetic institutions and on voluntary basis. The operational assimilation is done at many European national Met services. The use of EGVAP ZTDs has proven positive impacts on numerical weather prediction forecast scale. Using pressure and temperature estimates from meteorology, ZTD can be converted to integrated water vapor to create 2D maps of integrated water vapor for use by forecasters. This slide shows the impact of GNSS data on numerical weather prediction forecast. In the middle, you can see the hourly precipitation as observed by the radar. On the left, you have the precipitation forecast obtained without GPS, while on the right, the precipitation forecast obtained with GPS. The improvement achieved with GPS data is clear. The histogram on the left shows the impact per observation at various types of observation in the UK Met Office global and numerical weather prediction, with the GNSS delays having the second largest impact. It demonstrates that both that GNSS delays are useful and that numerical weather prediction system is far from being saturated with this type of humidity data. Additional GNSS ZTD will benefit the numerical weather prediction system. In more than 20 years of GNSS meteorology in Europe, outstanding results have been achieved due to a fruitful cooperation between the atmospheric and geodetic communities. Thanks to that, GNSS tropospheric products are now used for operational weather prediction applications like numerical weather prediction, nowcasting, and monitoring severe weather. There are challenges and developments in the fields to be faced in the next year. Several numerical weather prediction setup requires ZTD with improved timeliness. High-resolution numerical weather prediction will benefit from greater spatial resolution. It turns out that we have to move from hourly to sub-hourly processing. So far, only ZTD is assimilated. The impact of using ZTD gradients or slant is being tested with promising results. Unclear so far whether use of ZTDs adds skill relative to the use of ZTD gradients in NWP. As an alternative to NWP assimilation, GNSS tomography can be used to estimate the 3D refractivity field or the 3D water vapor fields, which can be used in numerical weather prediction assimilation or by forecasters. It requires a very high density of GNSS sites or additional data to constrain properly the tomographic solution. Forecasters will benefit from real-time integrated water vapor data from nowcasting of severe weather events. This requires real-time data, real-time products, and real-time processing. Regarding the impact of using gradients, I'm showing this very promising sensitivity experiment. Two GNSS networks with stations distributed at approximately 0.5 and 1 degree distance from each other were considered, as shown on the left-hand side. The results showed that assimilating ZTD led to an improvement in humidity. Moreover, where gradients are assimilated on top of ZTD from a sparsely distributed network, more information to correct the analysis data are given. This allows to maximize the humidity field improvement at places with fewer GNSS stations. Additionally, in the comparison with respect to ERA 5, it is observed that gradients performed at 1 degree network, red line, are roughly the same as the assimilation of ZTD alone at 0.5 degree, blue line. This study shows the sensitivity of tropospheric gradients and zenith wet delay during heavy local set precipitation events. The outcome is that GNSS is a useful and expensive tool to study the horizontal water vapor distribution before, during, and after precipitation event. This concludes my presentation. I sincerely thank all of you for your kind attention.